So, thank you, Mr. Chairman, for the kind introduction. So, we wait for the slides. So, as you already mentioned, today I will talk about the coexistence of these two topologically protected structures in ferromagnetic multilayers, more specifically in iron gadolinium multilayers. First, this is part of a bigger collaboration between the University of Vienna and University of Augsburg, and I work under the supervision of Klaus Albert and Dieter Süß, and we are the theory group. We do the micromagnetic simulations, and at the University of Vienna we work together with Michi Heigl and Manfred Albrecht, which perform the experiments mainly by Lorentz transmission electron microscopy techniques. I will briefly start with why we are interested in skyrmions or anti-skyrmions, give you a short introduction, what these, basically tell you what these solitons are in the first place. Then we will see our results about their coexistence in iron gadolinium multilayers, and then I will show you also the nucleation processes of the different topological spin textures, and we will also see how we can basically extend the range where these materials can coexist. So first of all, about the technological evolution of the spintronic devices. As we know, we right now need hard disk drives to store our data, and it's basically it gained a lot of momentum in 1988 with the discovery of GMR, which improved the reading of the magnetic bits. And in 2005, when exchange per megabyte was proposed, the storage areal density has increased, and the recording trilemma was broken, such that we were able to store more data in a very small space or area. But now recently we are struggling with the area density, and new solutions have been proposed, like the heat-assisted magnetic recording or microwave-assisted magnetic recording. But we also need memories to process data, and for the calculations in terms of RAM, so random access memory. And in 1995, the first non-volatile magnetic tunnel junction-based magnetic random access memory was designed. And this is a non-volatile one, which means that it's low energy consumption, because when we cut off the current and when we cut off the energy, it still stores the data. And in 2008, we had the first Racetrack Memory, where the information is basically encoded in the magnetic domains. And so we have the domain walls, and the basic idea would be to apply, as we also seen in the previous talk, that by spin polarized currents, we can then move along these domains. And then we can both store data in a three-dimensional fashion, but we can also have a memory which is non-volatile. And in 2013, Fair allies, so the same Fair who discovered the GMR, they designed, so they put the skyrmions on a track, and then they have designed a skyrmion racetrack memory. And in this case, the skyrmions are used to encode data information, and that's why a lot of momentum was gained in this research field, and this is basically one of the reasons why we're interested in the skyrmions as a possible application. So, and first let us see what these skyrmions are. And we have block skyrmions, and you can see the skyrmions as a local wheel of the magnetization. So in the core we have the skyrmion core, and then we have a continuous transition, so from this up state to the minus state. And this block skyrmion, basically, so if we draw a line along this direction, then we will have two block domain walls. We can also have an AL skyrmion, and this is a hedgehog skyrmion. So we have the skyrmion core, and then on the outside, then we have a negatively magnetized area. And again, if we draw a line along this, if you read the magnetization along this line, then we will have two nail walls. So. But we can also have a type 2 bubble, and maybe something very important, these topologically protected structures, they also have a topological charge. And in this case, the block skyrmion and the AL skyrmion, they both have a topological charge of +1. So, and then this means that we cannot annihilate them by a continuous, let's say, effect. So in this hedgehog, you can see that by a continuous transition of the spins, it's not possible to annihilate it. Then we have a type 2 bubble, which is a trivial bubble, basically, But then we also have the anti-skyrmion, which is the contrary to, let's say, it has the opposite topological charge. So this have a topological charge of +1, and this one has a topological charge of -1. So, and now if we come back to the skyrmion racetrack, in the idea of skyrmion racetrack, the skyrmions are used as bits. So then we have a bit of 1, and then whenever a skyrmion is missing, then we have 0. So basically the information is encoded in the distance between the skyrmions. And the skyrmions can then be moved by applying some spin polarized currents and some by spin torque effects. But the problem is that over long distances, they can basically shift from each other, and then the distances can vary such that we might lose some information. And these skyrmions are usually stabilized in system with the Dzieloszynski-Mourier interaction, or DMI, where the inversion symmetry of the system is broken. So, but as I said, the information is stored in the distance between the skyrmions, such that it does not as yet deliver the best results. So, to this case, we can also, as I said, so the skyrmions are stabilized by DMI. But in 2017, can you check? Okay. In 2017, Montoya ally, they published a very nice research where they were able to stabilize the skyrmions solely by dipolar interactions. So what they have done is that they have used iron gadolinium multilayers, and they have stacked them to obtain a certain thickness, about 70, 80 nanometers, and then under perpendicular applied external fields, they were able to image dipolar stabilized magnetic skyrmions. So, and then in the second phase, we have seen in the same year in a paper, in a publication by Jagannath that anti-skyrmions and skyrmions can coexist in Heusler compounds. So this is the material with D2D symmetry, which gives rise basically to the stability of the anti-skyrmions. So it was the one of the first experimental demonstrations of anti-skyrmions in Heusler compound. But they also showed that this material can host Bloch skyrmions, elongated elliptical Bloch skyrmions, which means that their coexistence is in principle possible, first. But then we can also have dipolarly stabilized skyrmion, which means that if you want to have our racetrack, we could, for example, instead of encoding the information in the distance between the skyrmions, we could use a skyrmion and an anti-skyrmion and then read out the magnetic field. So, as one of the possible applications, of course. So, and this is basically where we started. So we again have iron gadolinium multilayers, but this time what we are doing is that we are inserting an iridium layer. By this technique, we are able to create a multi-stack which further reduces the saturation magnetization as well as the uniaxial anisotropy constant. And in this case, we achieve a completely new range of magnetic parameters, which allows us to see multiple structures. The only problem would be that iridium is known to introduce a little bit of DMI in the system. I mean, you can also make it to introduce a lot of DMI, but in this case, it might introduce DMI. So we have to be sure that we understand the mechanics, the stabilization mechanism behind the structures that we see in the experiments. So, and in the experiments performed by Michi Heigl, and we see that we have counterclockwise Bloch skyrmions, first order anti-skyrmions, second order anti-skyrmions, clockwise Bloch skyrmions, and type 2 bubbles. And we have published our results together with what I will show in the later in a recent Nature Communications paper. And the fact that we were able to image using LTEM second order anti-skyrmion was the first experimental demonstration of this topological spin texture. Okay, so now we know that we have all these spin textures in our system, so we have the spin zoo. But now the question is, okay, what is the main mechanism that stabilizes these structures? And that's where micromagnetic simulations come into play, and that's where we basically come into play. And we wanted to see the conditions where the skyrmions and anti-skyrmions are stable. Okay, and what we do here is that we start from a rough parametrization. So we start with a box, 300 by 300 square nanometer, and then we have like a circle which we can give some sort of chirality to reassemble a skyrmion or an anti-skyrmion. And what we do is then we solve numerically the Landau-Lifshitz-Gilbert equation, and we basically so we include in the effective field term, we include contributions from the demagnetization field, uniaxial anisotropy field, then exchange field, and the Dzieloszynski-Mourier interaction, and of course the Zeeman field. So, and then we vary saturation magnetization and uniaxial anisotropy in certain ranges, as well as the DMI constant, to see the reasons where also to basically find out in which regions the the skyrmions or anti-skyrmions are stable. Okay, so and then in the case where we have an anti-skyrmion or a skyrmion, we calculate the topological charge, which is either -1 or 1 and 0 in the case when the topological structures vanish. And then we put this in phase diagrams, and then we vary the magnetic field. So, and then here we, for example, we vary saturation magnetization against the uniaxial anisotropy, and we see that we have a phase pocket where the anti-skyrmions are stable. So when we can insert enough iridium layers to reduce our magnetic parameters within these ranges, then we will have anti-skyrmions. These are results when we start from a rough parameterization of an anti-skyrmion, so it's easier for us to go to the local minima where the anti-skyrmion is stable. So, and in the case where, so in the other case, we just start from a rough parameterization of a skyrmion, and then we want to, we basically see that everywhere is just red, which means that skyrmions are then stable over these material parameters. And then we summarize our results in one phase diagram, which basically gives us a recipe where the skyrmions and anti-skyrmions are stable. And in this phase bucket, we have the coexistence of dipolarly or a little bit DMI stabilized anti-skyrmions of first order and skyrmions. And this is basically kind of a recipe. So if you know, we know the material parameters that we need. After this, it doesn't matter which materials we are using. We just need to come within this region, and then we could, of course, it's nothing is certain, but we could again see the coexistence of skyrmions and anti-skyrmions. But now the question is, are they dipolarly, solely dipolar stabilized, or by the Dirichlet-Morier interaction? And in this case, we vary the saturation magnetization and the DMI. So, and we see that for a certain, again, for a certain phase pocket, the anti-skyrmions are stable, but when we increase the value of the DMI too much, so, and 0.2 millijoule per square meter, it's already a very low value. So when we increase it too much, then the anti-skyrmions are not stable anymore. And they slowly transition to Néel skyrmions, as it's usually done, as the interface DMI usually stabilizes this type of topological texture. So now this is the first, basically it shows us that the skyrmions and anti-skyrmions more specifically should be stabilized by dipolar interactions. But then we go one step further, because until now we did single, let's say single particle simulations, right? But what we do now, it's large-scale micromagnetics. So we are simulating a 5,000 by 5,000 nanometer system with a thickness of 70 nanometers. And first we start with a system with DMI. At the vanishing external magnetic fields, we see that we have a certain domain morphology with Néel lines and Bloch lines. And this domain morphology basically will allow us to create a spin zoo when external magnetic fields are applied. And in this case, we have skyrmions, anti-skyrmions, trivial bubbles, and also a little bit reduced, smaller helices. We increase further the magnetic field. Then the trivial bubbles are not stable anymore. We only have skyrmions and anti-skyrmions, and then we increase the field further, and we end up only with skyrmions. And we repeat now without DMI. We want to see if this effect that we had in, the stability that we had in this small structure, if maybe it was, it was a finite size effect. We didn't apply any periodic boundary conditions. Maybe it was stable because we put it there as a rough parameterization, and it just stayed there. And then we do the same without DMI. Again, we have a very nice domain morphology. We apply field around the same field. We again have all the spin textures. We have trivial bubbles, we have skyrmions, we have anti-skyrmions, also again some helices. We apply the field as we increase the field, then trivial bubbles disappear. We still have anti-skyrmions and skyrmions. Then we increase the field further, and then we end up only with skyrmions. So in a system without DMI, with only dipolar interactions, we were able to stabilize all these topological textures. And now the question is, how do they nucleate?
2 minutes.
2 minutes, so I'll then speed up. So, and basically skyrmions, they are created when we have one helix, and then we apply a magnetic field, and they shrink down such that we obtain a counterclockwise or clockwise skyrmion. In the case of an anti-skyrmion, we need a tripod. So we have 3 legs. And when we have these three legs, we again apply the magnetic field. We basically cut off the one of the legs, then the second one, the third one, and then we end up with an anti-skyrmion. This is in a system without DMI. In the system with DMI, just the same happens. The only difference would be that in this case, when we have a four-leg system, let's say, yeah, four-leg domain or helix, we are able to stabilize a second-order anti-skyrmion. So, but the presence of the second-order anti-skyrmion in a system with a little bit DMI, it does not mean that it's only stable with DMI, because this is very rare. Even in the experiments, we have seen it only a couple times. Another question is, how can we further extend this range of material parameters that can be used to show this coexistence? And in this case, we can basically make use of a concept like nucleators and stabilizers, which means that we can have a material with low saturation magnetization, as in this case, and then a material with a high saturation magnetization, which normally would not host magnetic skyrmions or anti-skyrmions. And then we can layer them up, and then we can see that we obtain again the same domain morphology, which will allow us to stabilize some of the structures. And now when we further would apply a magnetic field, we would again see the topological textures. So, and we have published our results recently in a Nature Communications paper, and I would like also to thank to all the other contributors, as it was a big common effort. And as a quick summary, we can tell that we have investigated iron gadolinium multilayers, where by the insertion of additional iridium layers, we were able to reduce the magnetic parameters in such a way that skyrmions, anti-skyrmions, and trivial type 2 bubbles were dipolarly stabilized. And we have proved basically their coexistence. We have seen that yes, that they are dipolar stabilized, and that now we have a recipe which materials and which material parameter ranges we can use in order to to basically again see this coexistence. And then we have seen that it's not only that we have to use one material, but we can make use of mixed concepts like nucleators and stabilizers in order to achieve the same effects. Thank you very much for your attention, and I'm happy to receive questions.
Thank you very much. We have a question there.
So can we have annihilation of skyrmion and anti-skyrmion? Because there is some level of similarity of skyrmions to vortices in superconductor, right? At some point, both have kind of topological charge. So if there is annihilation of vortex and anti-vortex, there is some release of energy. Do you expect similar process to take place, and what would be the channel of energy release?
Thank you for the question. So I think it's a bit different than superconductivity, where we have the vortex and anti-vortex, because these are their spin. Okay, so we have here these are the orientation of the spins is completely different. So then of course they can, like, you can annihilate, let's say when you want to annihilate the skyrmion itself, yeah, you have to go over the so-called Bloch point. So because it's a topologically protected charge, so you can either like push it out of your sample by applying by spin polarized course or something similar. But if you want to annihilate one single skyrmion, that's very, very different, because these are topologically protected charges. So, and if you have like, let's say if skyrmions and anti-skyrmions, basically they would scatter into each other, yeah, they would bump into each other. They don't annihilate like the vortex and anti-vortex pairs in superconductivity, because they have these different spin textures, which basically creates different magnetic fields around them, and then they repel each other. So they even two skyrmions would repel each other. They can join, but there would be still some attraction or repulsion forces. So skyrmions are more probable. So it's they have this topological protection, and they are also protected basically by their different magnetic fields that they create based on their spin textures.
So your claims that they cannot annihilate?
I mean, this is what I think right now, because I didn't try it out, but it would be interesting to just push them into the same direction and see if they annihilate. But as I said, so I believe right now, because I didn't simulate this, I believe that they have this magnetic field around them that is different. It's in the same direction, but it's different, or opposite directions.
Well, it's the same with superconducting.
Maybe we need to.
Okay, maybe we can
stop
discuss
here.
afterwards too.
It's a nice discussion, but for the coffee time.
Yeah.
Then thank you very much. One more? Okay, short question.
So you were computing that you can also stabilize these fermions in when you have absence of the EMI, but this I don't really get. So how you set the chirality of the antiskirmion, or I mean the topological charge of the antiskirmion, because you don't have a symmetry breaking mechanism. Yeah, exactly. So at 0 the EMI. So how do you set the topological charge that you would have in the system?
But how it's like stabilize itself, or do you mean just because of how?
I mean, I would expect to have antiskirmions with different chirality, and in the end, the topological charge of the.
Yes, the chirality is basically they're given is by the domain. So because you basically have these domain walls in your system. So you have your helices, and then you apply magnetic field, and then along these block lines, you just reduce their size, and then you just shrink them down to a skirmion. So the chirality is given by the domain morphology itself.
Okay, but at the beginning you have domains with different structures. So
yes.
So let's say in average you would have antiskirmions with different chirality in the system. So that's what I'm saying, that you in the end, I guess you would have different topological charge.
Exactly, all these we are clockwise, counterclockwise.
Okay.
They can have all these different conditions because exactly for the reason we discussed.
Okay.